In this video, we're learning how to find the volume of a solid of revolution using the method of cylindrical shells. We'll start by looking at the formulas that you can use and go over the steps you can follow to solve these types of problems. We'll then work through 4 examples so that you can see how the method works in each typical situation. Be sure to download the free guided notes to follow along, highlight the formulas, and work through the examples with me. Let's go over the formulas and steps that you can follow for finding the volume of a solid of revolution using cylindrical shells. A solid of revolution is obtained by rotating a region in the plane about an axis or a line. Let's first go over the formula for rotating a region about the y-axis. In this first diagram, we have a region that sits on the x-axis. When we rotate this region about the y-axis, we get a solid of revolution that has cylindrical shell cross-sections. The volume of this solid of revolution is equal to the integral of this cross-sectional area from x is equal to a to x is equal to b. This cross-sectional area is a rectangle. You can think of it as the label that's wrapped around a cylindrical can. The width is equal to 2 pi r, that's just the circumference of the circle, and then the height is equal to h. If we look back at our diagram, you can see that the radius is going to be x and the height is going to be y, so our cross-sectional area is just 2 pi times x times y. The volume for the solid of revolution can then be found using this formula. It's equal to 2 pi times the integral from a to b of xy times dx. The thickness of each shell is dx. In our next diagram, we have a gap between the region and the x-axis. When we rotate this region about the y-axis, we also get a solid of revolution that has cylindrical shell cross-sections. The cylindrical cross-sectional area is still 2 pi rh, and r, the radius, is still x, but now the height, shown right here, is going to be the top curve minus the bottom curve, and then we still have a thickness of dx. Let's now go over the formula for rotating a region about the line x is equal to a. A line x is equal to a is a line that is parallel to the y-axis. The formula for our volume is really similar to the formulas that we just looked at, but now the radius is just written as r, and it is the distance from the curve to the revolving line, and then the height y is the distance from the x-axis to the curve. If the line that you're rotating about lies to the right of the region, the radius is a minus x, and if it lies to the left of the region, the radius is x minus a. You don't need to memorize those formulas if you just draw a diagram for each problem that you're solving and remember these definitions for y and r. Let's now go over the formulas for rotating a region about the x-axis. These formulas are very similar in structure to the formulas that we just looked at for rotating a region about the y-axis, but now the integration is in terms of y instead of x. In this first diagram, we have a region that sits on the y-axis. If we rotate this region about the x-axis, we get a solid of revolution that has cylindrical cross-sections. Just like before, the volume of this solid of revolution is equal to the integral of the cross-sectional area from c to d times dy. The reason that there is a dy is that the thickness of each cylindrical shell is equal to dy. This cross-sectional area is again a rectangle, and it's equal to 2 pi rh, but now the radius is equal to y, and the height of the rectangle is equal to x. This gives us the formula of the volume is 2 pi times the integral from c to d of y times x times dy. In our next diagram, we have a gap between the region that we're revolving and the y-axis. When we rotate this region about the x-axis, we again get a solid of revolution that has cylindrical cross-sections. Everything is the same as the formula that we just looked at, but now what's different is the height. This height is equal to the curve on the right minus the curve on the left. And then everything else is the same. Let's now go over the formula that we need to use when we revolve a region about a line y is equal to b. A line y is equal to b is a line that is parallel to the x-axis. The formula for the volume of revolution is the same as the ones we just looked at, but now the radius is just written as r. If the line that you're going to be rotating about lies above the region that you're given, r is equal to b minus y, and if the line lies below the region, then r is equal to y minus b. If you don't want to memorize those formulas, just remember that x is the distance from the y-axis to the curve that you're given, and then r is the distance from the curve to the revolving line. Since finding solids of revolution is complicated, just to make things easier, I've written down 5 steps that you can follow to solve these problems. The first thing that you're going to do is graph your given curves, and then you're going to find the points of intersection. From the graph, you can determine the value for the radius, or radii, if there's a gap between the region and what you're rotating about. You can then choose the correct volume formula, and then all you have to do is evaluate the definite integral. We are going to go over 4 examples so that you can understand how to apply these formulas and steps. We're going to walk through an example where we find the volume of a solid of revolution that's obtained by rotating the region bounded by the given curves about the y-axis. In this problem, we are going to be using cylindrical shells. The curve that we're given is y is equal to 2x squared minus x cubed, and y is equal to 0. Just to make this easier, I went ahead and graphed both of these curves, and you can see the region enclosed by these curves in green. You may have previously studied disks and washers, and what sets this problem apart is you can't use disks and washers because in this region, the curve on the left is the same as the curve on the right. So cylindrical shells are the best to use. We're going to be revolving this curve about the y-axis, and the cross-sectional area is cylindrical shells. The thickness of each shell is dx, so we are going to be integrating with respect to x, which means the first thing that we need to do is find the x value for the points of intersection. To do that, we just have to set the curves equal to each other. So we're going to say 2x squared minus x cubed is equal to 0. We can factor out an x squared, and that leaves us with 2 minus x is equal to 0. And we can see then that x is equal to 0 and x is equal to 2. Let's mark these on our graph. Here we have x is equal to 0, and here we have x is equal to 2. So those are going to be our limits of integration. Now what we have to do is look up here at our formula. Our formula for the volume of the solid that we're going to get is 2 pi times the integral from a to b, that will be from 0 to 2, r times h dx. What we need to do now is find r and h. This is our radius, and this is our height. The radius is the distance from the curve to the y-axis, and that is equal to x. And then h is the distance from the x-axis to the curve, and that is equal to y. Now we can go ahead and write down our formula. Our volume is 2 pi, the integral from a to b, r times h dx. So this is 2 pi, our a is 0, and our b is 2. Our radius is x, our height is y, and we're integrating with respect to x. We now need to substitute in that y is our curve 2x squared minus x cubed. This gives us our volume is 2 pi times the integral from 0 to 2. We have x, and then we have 2x squared minus x cubed dx. Before we integrate this, let's simplify what we're going to be integrating. This is 2x cubed minus x to the fourth times dx. Now we can go ahead and integrate this. The integral of 2x cubed is 2x to the fourth over 4. And then we subtract off x to the fifth over 5. And we're integrating this from x is 0 to x is equal to 2. Now let's substitute in that x is equal to 2. So we have 2 times 2 to the fourth all over 4 minus 2 to the fifth over 5, and then we subtract off 0. This gives us 2 pi. 2 to the fifth is 32. So we have 32 over 4 minus 32 over 5. Let's pull the 32 out. So this gives us 64 pi. And then we have 1/4 minus 1/5. We will get a common denominator of 20. And then we get 5 minus 4 on top. So this is 64 pi over 20. And each number is divisible by 4. So this gives us an answer of 16 pi over 5. Our volume then is equal to 16 pi over 5. We're going to walk through an example where we are going to find the volume of a solid of revolution by revolving a region about the line x is equal to a. In this problem, we are going to be using cylindrical shells. Our region is bounded by the curves y is equal to x minus x squared and y is equal to 0, and we're going to be revolving this region about the line x is equal to 2. The first thing that you want to do when solving this type of problem is to graph the curves. I've already done that just to make things easier, and I've also graphed the line that we're going to be rotating our region about. The formula that we're going to be using is the standard formula for using cylindrical shells for rotating a region about a line that is parallel to the y-axis. We're integrating with respect to x because the width of our cylindrical shell is equal to dx. The first thing that we want to do is find the x intersection points, and those are going to be this point right here and this point right here. We can find that by just setting our two curves equal to each other. We have y is equal to x minus x squared, and we're going to set that equal to y is equal to 0. We can factor out an x, and this leaves us 1 minus x is equal to 0. So we get that x is equal to 0 and x is equal to 1. We'll go up here and label this point 0 and this point 1. Now what we need to do is find r and y. R is the distance from our curve to the line that we're revolving about. So this distance right here is going to be r. To find what r is equal to as a function of x, we need to notice that this distance right here is equal to x. Because this distance here is equal to 2, we can say that x plus r is equal to 2, and that gives us a formula for r, and it's equal to 2 minus x. Y then is this distance right here that I'm marking in red, and it is the distance from the x-axis to the curve. We can just write down that y is x minus x squared. Now we can go ahead and set up our integral. We'll write down the formula first. Our volume is 2 pi, the integral from a to b, r times y times dx. We'll substitute in that a is 0 and b is 1. Our radius is r is equal to 2 minus x. And then y is equal to x minus x squared, and we have dx. Before we integrate this, we are going to multiply out what we're integrating. We can use the FOIL method, multiply the first terms, which is 2x. We'll multiply the outer terms, which is minus 2x squared, and then the inner terms gives us minus x squared, and then our last terms gives us plus x cubed dx. Looks like we can combine our x squares. So let's do that before we integrate. This gives us 2x minus 3x squared plus x cubed times dx. Now we can go ahead and integrate. Our first term is 2 times x squared over 2, so the 2's will cancel, and then minus 3x cubed over 3 plus x to the 4th over 4, and we're evaluating this from x is equal to 0 to x is 1. Let's see what we get. We'll substitute in that x is 1, so we get 1 minus 1 plus 1/4. And then when we substitute in x is 0, we get 0. So this is really nice. This just turns out to be 2 pi divided by 4. So we get an answer of pi divided by 2. And that tells us that our volume is equal to pi over 2. Let's now walk through an example where we are going to find the volume of a solid obtained by revolving a region about the x-axis, and we're going to use cylindrical shells. The curves that we're given is x is equal to 1 plus y squared, x is 0, y is 1, and y is 2. The first thing that you want to do when you're solving this type of problem is to graph these curves. I've already done that to make things easier. Here's the curve. X is equal to 1 plus y squared. Here's the line y is 2. Here's the line x is 0. And here's the line y is equal to 1. So the region that we're going to be revolving is the region that is enclosed by that curve and those 3 lines. We're going to be rotating this region about the x-axis, and we're going to use cylindrical shells. And here's the formula that we are going to be using. What we need to do first is find the limits of integration. We are integrating with respect to y because the thickness of each of our cylindrical shells is equal to dy. The first thing that we need to do is to find the points of intersection of all of these curves. And because we're integrating with respect to y, we need to find the y value. Because 2 of our curves are lines, we actually don't have to do anything. And we can see that we're going to integrate from y is equal to 1 to y is equal to 2. So let's just mark over here c is equal to 1 and d is equal to 2. Now what we need to do is find r and h. Our radius is right here. I'm marking this in blue. And it is the distance from the curve to our axis of rotation, which is the x-axis. So this is just equal to y. And then the height, which I'm going to mark here in red so that you can see it, and that distance, we'll mark this up here, is h is equal to x. Now we can go ahead and write down our formula. I'm going to write the general formula first. This is 2 pi, the integral from c to d of r h dy. Now we can substitute in what c and d are. C is 1, d is 2. Our radius, let me highlight this so you can see it, is equal to y. And then our height is equal to x. And we're integrating with respect to y. Now what we have to do is substitute in what x is. X is given by our curve 1 plus y squared. And let's go ahead and put that in. We get 2 pi, the integral from 1 to 2, y times 1 plus y squared dy. Before we integrate, let's go ahead and multiply this out. We have 2 pi times the integral from 1 to 2. Inside, we have y plus y cubed times dy. Now we can go ahead and integrate. This is 2 pi. We have y squared over 2 plus y to the 4th over 4. And we're evaluating this from y is 1 to y is 2. Let's first put in that y is 2. 2 squared is 4, so we have 4 over 2. 2 to the 4th is 16, so we have a 16 over 4. And then we subtract off 1/2 and 1/4. Let's combine our fractions. We have 4 halves minus 1/2, so that's 3 halves. And then 16 over 4 minus 1 over 4 is 15 over 4. Looks like we can get a common denominator of 4. So this is 6 plus 15. We can cancel the 2 into the 4. So this gives us 21 pi divided by 2. And this tells us that our volume of revolution is equal to 21 pi over 2. Let's walk through an example where we are going to be finding the volume of a solid of revolution by revolving a region about a line y is equal to b, and we're going to use cylindrical shells. Our region is enclosed by the curves x is equal to 1 plus y squared, x is equal to 5, and y is equal to 0. And we're going to be revolving this region about the line y is equal to 3. The first thing that you want to do is to graph all of these curves. I went ahead and did that just to make it easier. Here's our curve. X is equal to 1 plus y squared. Here's our line. X is equal to 5. And then our line, y is equal to 0. The region that we're looking at is the region that is enclosed by our curve and those two lines. We're now going to be revolving that region about the line y is equal to 3. This line is parallel to the x-axis, and we're going to be using cylindrical shells, which means that the thickness of our shell is going to be equal to dy. And our formula over here will integrate with respect to y. The first thing that we need to do is find the points of intersection. In other words, we want to find the y value of our limits of integration. Looking at our graph, we are going to integrate from y is equal to 0 to y is equal to that point right there. And that's the point that we need to find. So to find that, what we're going to do is we're going to set our curve 1 plus y squared equal to our line x is equal to 5. This gives us y squared is equal to 4. So we get y is equal to 2. We're only interested in the positive one. Let's go ahead and label this. So let's say here y is 0 and y is 2. Now what we need to do is find the radius and height. The radius is the distance from the curve to the revolving line. So that's this distance right here. We'll label that as r. We know that this distance here is equal to y. So we can find r by writing down that r plus y is equal to 3. 3 is this distance right here. And this tells us that r is equal to 3 minus y. I'm going to highlight that because we are going to need that in a minute. Now we need to find h. I'm going to mark h in red, and it is this distance right here. So let's mark this as h, and then we'll come up here, and let's figure out what h is. This distance here is equal to x, so x plus h is equal to 5. We can then solve this for h, and we get that h is 5 minus x. And let's highlight that because we will also need that. Now we have everything that we need to set up our integral. Let's write down our formula first. Our volume is 2 pi times the integral from c to d, r h dy. We found that our limits of integration were between 0 and 2, so we're going to integrate from 0 to 2. Our radius we found was 3 minus y, and if we look back up top here to the right, our height is 5 minus x dy. Now we need to substitute in what x is. X is given by the curve 1 plus y squared. This gives us a volume equal to 2 pi of the integral from 0 to 2. We have a 3 minus y and a 5 minus the quantity 1 plus y squared. You just have to watch your parentheses there. Before we integrate, let's simplify what we have inside. This is 3 minus y, and we have a 4 minus y squared dy. Now, we definitely don't want to integrate yet. What we have to do is multiply everything out. We can use the FOIL method to do that. Let's multiply the first terms, and then the outer terms, and then the inner terms, and then our last terms. dy. Now it looks like all 4 of those terms are different, so we can't do any more simplification. So let's just go ahead and let's integrate. This is 2 pi. We have 12y minus 3y cubed over 3 minus 4y squared over 2 plus y to the 4th over 4. And we're evaluating this from y is 0 to y is equal to 2. Let's see what we get. We have 12 times 2 is 24. Our 3's are going to cancel. So we just have minus 2 cubed, so this is minus 8. And then we have a minus 2 times 2 squared, which is 4. And then we have 2 to the 4th, which is 16, divided by 4, and subtract off 0. This just gives us 2 pi times 24 minus 16 plus 4. This gives us 2 pi times 12 for a final answer of 24 pi. 24 times pi is what the volume of our solid is equal to. And that's it. You've learned how to use the cylindrical shells method to find the volume of any solid of revolution. To really master this method, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.